the kinetics notes that I promised you guys. Starting here with reaction mechanisms. Let's write it in blue today. Basically, what a reaction mechanism is. The majority of chemical reactions don't occur in like one, bam, step. They're done. It's more like, okay, first this has to happen, and then this happens, and then this happens. Think of it like, a chemical Rube Goldberg machine or something. And the elementary step, it would be the individual steps throughout the mechanism itself. And there's this great word, I love this word, molecularity. Fantastic word. Definitely make sure you use that word at some point in conversation today. But basically all it is the number of molecules that's participating in a particular elementary step. And so if you have a unimolecular step, then that means it's just one molecule reacting on its own. Maybe it's like falling apart, or maybe it's, switching a bond, or, something like that. And the rate is considered to be first order. So unimolecular, first order. Bimolecular means you need to have two molecules slam into each other in just the right way, and so it's considered to be a second order reaction. You can have a termolecular, I guess maybe tetramolecular, or maybe quadmolecular. I don't know what fourth would be, but that would be even more rare. And the reason that this is so rare to have a step that requires the reaction of three molecules is because think about it. These three molecules all have to hit at the same time and facing the right direction in order to react. And the probability of them hitting just right is so low. And you know how nature likes to do things the easy way? A termolecular step is not the easy way. There's got to be a unimolecular, bimolecular step in there for an elementary step that nature would definitely prefer. If a reaction is dependent on a termolecular step, chances are that reaction is going to be pretty slow. So a reaction mechanism is just basically written as a series of steps that will add up to the overall reaction. So you can see this right here is our overall reaction. And this is a possible mechanism. And I'm going to point a couple of things out here. I'm going to make sure I'm not getting ahead of myself. I am getting a little bit ahead of myself. That's okay. I'm going to point out a couple of things here. If you take all three of these reactions and you add them up, you can see just kind of, first let's start here with the reactants. Okay, I've got 2 A's. Then I've got 1 A2. I've got 2 B's. And then I have this thing an A2B. And then that's going to turn into my products. So I have an A2 plus an A2B plus an A2B2. And then if you cancel out the things that are the same on both sides, so like we have this A2 here, we can cancel that out. We have an A2B, we can cancel that out. And you'll notice that what's left over adds up to the overall reaction. So this is just a possible mechanism. Is it right? Who knows? And then the rate laws for each of these reactions are written here, and you can see that. And the fact that this is a 2 is not because of the fact that you have like 2A turning into A2. It has to do with the rate order with respect to A. And so kind of coming in here, you noticed that this A2 here got canceled out, and then I'm going to switch colors just to make this stand out a little better. This A2B at some point got canceled out. And I want to point out these two guys have very specific meanings. Notice that A2 was produced and then used. And a substance that is produced and then used is an intermediate. A chemical species just refers to any compound or element that is, in the reaction. And so the intermediate is the guy that is first produced and then used up in a following step. And I should not have, A2B is also produced and then used. The opposite of this, the opposite of an intermediate, would be something that is first used in one step and then produced in another step. And that's what a catalyst is. And so I actually don't have an example of a catalyst up in here, but I think I maybe have some in the example problems that I do later. And then the rate determining step, the one that determines how fast this reaction goes, is the one that goes the slowest. Because if you think about it, I always like to think of the I Love Lucy episode where you have Lucy and Ethel and they're at the chocolate candy factory. And you've got the candies coming out that little door on the conveyor belt, and then Lucy and Ethel are supposed to wrap them in some kind of plastic and then send them on their way. Well, it ends up being that Lucy and Ethel are the rate determining step. The amount of candies that actually goes on to be bagged is determined by how many that they can wrap, not determined by how many can come out that little door thingy. And so the rate determining step is the one that's the slowest. It's another way of thinking of it is you're only as strong as your weakest link. Well, the weakest link in a reaction mechanism is the slowest one. So you can only go as fast as your slowest step goes. And so it's the one whose rate law is used as the rate law for the whole entire equation. And so let's say that, this first step here was the slowest step, then the rate law for this reaction would be this guy. And if you notice, B isn't even in here. And what that means is that if this was the actual rate law for the equation, then that would mean that the rate is not dependent on the concentration of B at all. It's only dependent on the concentration of A. Let's see, definition of a catalyst. It basically just makes the reaction go faster. It's not the definition is that it's not used up in the reaction, but it actually, I'm just going to give you a skeleton of a reaction here. So if you have, compound A plus compound B yields compound C plus compound D. This is the overall reaction here. Actually, no, I don't want to do it that way. Let's just say A plus catalyst yields B. Well, what's actually going to happen is A plus the catalyst yields, say, some third compound. We'll call him C. And then C plus B yields the catalyst. Or C plus, let's see what needs to be canceled out here. I don't know, C plus, let's just throw another A in there. I can't do B because that's going to cancel it out. Yields the catalyst plus B. And what happens here, whoops, is that, so this is the overall reaction. And so we have to have the catalyst come out the other side. And so it looks like the catalyst wasn't ever used. It's just, there in the reaction, kind of like being a coach, encouraging its players to do their thing. But what's actually happening is it gets used up in this step and then produced in this final step. And in this way, we would actually have 2A here. The C would get canceled out, so the C would be an intermediate. In that it was produced and then used. The catalyst is used and then produced. And it can work a couple of ways. It can either, it basically just changes the slowest, whatever the slowest step of the reaction is, it changes it to something that's faster. Or it could lower the activation energy. And then that's going back to the energy graphs that were in part 1 of the kinetics notes. So that's actually all for the kinetics notes that I have. For more practice, then you can watch the kinetics practice problems. So y'all have a great day.